In this lesson, we're going to be still looking at objective 8.5 titrations, but this part of the video, part 2, we're going to be looking at some example problems that you could expect on the test. So here, let's look at this example. It says, let's try an example on sketching a titration curve. So they told us a 30 milliliter sample of a 0.05 molar solution of hydrogen carbonate was titrated with 0.05 molar hydrochloric acid. And we should sketch the expected titration curve given the following information. So first things first, I've highlighted everything about the hydrogen carbonate as well as the hydrochloric acid. But let's first also just write the reaction of what's happening. So I have hydrogen carbonate being titrated with hydrochloric acid. I'm going to immediately put H3O positive because when we do titration problems, we need to go directly from the HCl to H3O positive because that's going to be this thing that's reacting, not the Cl minus. And it's going to make H2CO3 plus water. So the HCO3 is going to be my weak base, the H3O positive, my strong acid, and we will be making a conjugate acid. So H2CO3 and HCO3 minus are conjugate acid base pairs. So they gave us pKb, they gave us the starting pH, and the pH at the equivalence point. So let's first, I'm going to quickly change this to H3O positive. So here, what's happening is based off the titration, your HCO3 minus is going to be your analyte, and the H3O positive is going to be your titrant. The reason I know that is your titrant will always be found on the x-axis. Remember, the titrant will be in the burette and it will be added into your flask. Your flask will contain whatever your titrant is, which in this case is the hydrogen carbonate. So here, the starting pH is 9.53. Also, look at the starting pH. If this was a strong acid, we would be seeing a pH that was much lower, but here it's 9.53, which makes sense for this weak base. So here, I know the labels aren't the best, but just kind of estimate where you think 9.5 would be. So I'm just going to say, what about right here? 9.53. There's our first point. It then tells us pK. So I got the starting pH. Now look at pH at equivalence. So at equivalence point, that is when the moles of my weak base and the moles of my strong acid equal each other. So here, this also, pH of equivalence, don't stress out that it's not a pH of 7. pH of 7 would be if this was a strong acid, strong base. But here, remember, if these are the two reacting, an equivalence point means that the moles of acid and base react and they'll be limiting reactant. All that's left is going to be your conjugate acid and water. Key word here, conjugate acid. Acidic things have a pH less than 7, so it makes sense that our equivalence point will be less than 7. So I'm going to say right around here is my equivalence point. I did not use the first line just because when it comes to a weak, strong titration, we are going to need to use the equivalence point, okay? Or half equivalence point, excuse me. So here, this is volume for equivalence point. And this will be half volume equivalence point, which will come back in just a second. I do want to note that we should also know what the volumes are, so we can add that right next to those lines once we figure that out. So let's figure out maybe some more information. So we were told everything about the hydrogen carbonate. We were told it was 30 milliliters to start, and we actually know what the solution for the analyte is. And this is totally okay that we figured out analyte. All of your problems don't have to be that you have to solve for the unknown. The analyte would just be the one that we started with. In this case, we were not told the volume of hydrochloric acid that was added. So sometimes you might solve for the unknown concentration. We may also solve for how much volume was added. Totally fine. So H3O positive. We do not know how much volume was added at equivalence point, but we do know its concentration. So here, let's use M1V1 equals M2V2, because we can use this when we know something has reached equivalence point, because it will be a 1-to-1 ratio. So here, it doesn't matter what side you put everything on. And honestly, if you're solving this problem, you already know the answer, totally fine as well. But if this is the AP test, they're going to want to see how you got that value. You probably already know it, but the volume is going to be 30 milliliters. So here you need 30 milliliters of your titrant to reach equivalence point. So I'm going to write 30 milliliters. I'll actually just leave it as 30. So here we need 30 milliliters to reach that equivalence point. Now let's talk about the half equivalence point. So we know at a half equivalence point, I'm running out of room already. Here, I'm going to erase this and add this up here just to give me some more space. So at half equivalence point, please note anything before you reach equivalence point right here, everything over here will be involving a buffer. And remember, a buffer is going to represent my two weak things. My two weak things being the HCO3 minus and the H2CO3. So at half equivalence, I'm going to use concentration. Concentration of HCO3 minus, sorry, my 3 looks bad. Still looks bad. Here we go. Equals concentration of H2CO3. So using Henderson-Hasselbalch, we know if those equal each other, it will be a log of 1, which is 0. All right. So the little bit of an issue when it comes to this first step right here. So hold on, let me show that this will get rid of. So here we know pH equals pKa, but based off the problem that we're starting with, they gave us a pKb. So you have two options. You can quickly convert that pKb to a pKa, totally fine as well. Or you can just think of it as, well, if POH equals pKb, 14 equals pH plus POH. So here, if I know pKb is 7.63, I can solve for pH. So pH is 14 minus the 7.63, and I get pH as 6.36. All right. Sorry, I know I did a lot of different things for this problem. I'll keep those separate. All right. So at half equivalence, this is half the volume. So half of 30 would be 15. And we just found that it was going to be 6.36. So here, I'll do something around here. So here, honestly, the points that they truly will be looking at is your initial pH as well as equivalence point. Everything else is going to be completely fine. I might actually just bring this one down a little bit lower. Here we go. So here, I'm just going to show this and like that. Again, it doesn't need to be perfect, okay? Probably could have brought that dot maybe a little bit down further, but that's totally okay. But again, this area will be where you have a buffer, and then anything past equivalence will be your excess strong acid. But technically, this little plateau is that buffer region, like the most effective buffer. But everything in that yellow, you would just use Henderson-Hasselbalch to do. Okay, moving on. A few little main takeaways before we move on. For a weak base, half the volume of equivalence point, pH equals 14 minus pKb. That is just like that last part that I just did right here. Here, this is when you start with a weak base and a strong acid titration. Just knowing that you can't just do, oh, negative log of Kb, or like just because this technically is not the correct pH. Next, at a volume less than half equivalence point, the concentration of base is the more dominant species. So let me zoom out to look at my titration again. So here, a volume less than half equivalence, it's talking about this portion right here. You're going to have more of the base, okay? Just because we know at this point right here, weak base equals conjugate acid. So anything to the left, you'll have more base, and anything to the right will be more conjugate acid. Till we get to this point right here, we will just have conjugate acid. But we don't need to annotate to this point. I'm just trying to talk about main points. And then at half equivalence point, moles of conjugate acid equal moles of weak base. All right, moving on. I have one FRQ that I will do with you, and then I have a longer FRQ at the end that I will have you pause the video and try, but let's do this one together first. So, answer the following questions regarding a 0.05 liter solution, a 0.1 molar solution of weak acid HF, and they gave us the Ka value. The solution is titrated with 0.1 molar NaOH, and they told us the pH at the equivalence point is approximately 10.20. So we need to first calculate the volume of base needed to reach equivalence point. So let me just quickly, before I get too deep into the problem, I'm going to highlight the things we know about HF and then what we know about the base. And we do also know the pH at equivalence. All right, so at equivalence point, we know moles of HF equal moles of OH minus. So anything referenced towards equivalence point in a titration, you should be using the dilution equation. Now for our test, we will use dilution because it's a 1-to-1 ratio. But if we were doing something with, like, let's say sulfuric acid, H2SO4, we cannot use the dilution equation because it would not be a 1-to-1 ratio, it would be a 1-to-2. So let's add everything about the acid on the left and everything about the base on the right. So concentration for the weak acid is 0.100 molar. Volume is 0.0500 liters. And then the concentration of the strong base is 0.100 molar. And we are solving for volume. And again, just like the previous problem, if you can already figure out what it is, awesome, but make sure that you still solve for it. So here we get 0.0500 liters, or you could say you got 50.0 milliliters. All right, next problem. We're going to calculate the pKa for the weak acid. So let's look again at what they gave us. They gave us a Ka. So here with a Ka, we can just take the negative log of that to get pKa. So pKa is a negative log of Ka. So here, negative log of 6.8 times 10 to the negative 4. I end up getting that the pKa is 3.2, or you input 3.167. I wouldn't worry too much about sig figs for just this part right here, just because 6.8 was a given to us, a Ka, and that's not something that really can be calculated unless you use a lot of different data. This was given to you. Again, we'd probably have to use it later, maybe if this had multiple parts to it, so don't try to use such a rounded value, okay? All right, part C. We're going to determine the pH of the original acid solution. So, you know, they did tell us equivalence pH, but that's not going to help us figure out the original acid solution pH. So here, this is just going to be, I ran out of room. This is just going to be just like an objective 8.3 problem. I'm going to write that just right here. And so here, if we're just trying to solve for the pH of the original acid, let's first write out what the original acid in weak equilibrium would look like, all right? So let's fill out an ice table, because the whole thing is if we want a pH, we need to know the hydronium. But the hydronium isn't going to be a 1-to-1 ratio with the concentration of HF, which we know the concentration of HF is 0.100 molar. Because HF does not dissociate 100%, it'll be less than that. So using the Ka, we can, in an ice table, we can figure out hydronium. So ice table minus X, 0, 0 plus X. And so now I have all of my values that can be added to my Ka expression. So remember, Ka is taking the conjugate multiplied by hydronium all over the weak acid. And now I'm going to plug in the values that I know. So although right now that K value is times 10 to the negative 4, please note that you'll never have to do the quadratic equation. So let's assume negligible X. So that leaves us with 6.8 times 10 to the negative 4 equals X squared all over 0.100. So we're going to multiply 0.100 to the other side, get X by itself by taking the square root. So here, X, which will be our hydronium, will be the square root of the Ka multiplied by the original acid concentration. Here, after calculating, you should get 0.008246. Do not round too much because we have not finished the problem yet. And then to finish it, since this will be hydronium, pH is the negative log of that value. So I get the pH as 2.08. And this will be the pH of the original acid, HF, before it was titrated. All right, we're going to move on to the last problem. It is a long problem. I do want you to pause the video and please try this out yourself. Even if you can't get all of it, just try each one, see if you're able to do it. And then click play, and I'm actually going to work out this problem after B double I. I will start teaching and going over the problem as I go after B triple I. So the first part, writing out the K expression, you should get Kb equals the conjugate acid multiplied by hydroxide all over the diethylamine, that weak base. Okay. Next part tells us the pH of a 40 milliliter sample of 0.85 molar diethylamine is 12.522. So we want to calculate the molarity of hydroxide in the solution. And this is all pretty much before anything has happened, okay? So if you're given a pH, don't overlook this, all right? Because the first thing we can do is find the pOH, which can figure out the hydroxide by taking 10 to the power of negative pOH, which I did, and I got 3.32 times 10 to the negative 2 for hydroxide. And again, this is all before anything's happened. This is just your diethylamine chilling in weak equilibrium. Next part, it wants us to calculate Kb. So I wrote an ice table to help kind of dissect this a little bit. So filling out an ice table, you can see after filling it out, that X that I get for hydroxide is actually the same value from Bi. So that 3.32 times 10 to the negative 2 is going to be the X value. So I plugged in X, you can see my pink arrows, and then I plugged all of that E row into the Kb expression, which you can see off to the left. And then after calculating, I got Kb as 0.00135. Or 1.35 times 10 to the negative 3. All right, so B, triple I, and so on, I will do as I go with you. I just wanted you to get the first part under your belt. If you already got, if you want to try the rest of the 3 parts, you're more than welcome to, but I'm just going to go over this with you. So part B, triple I says determine the pH at the half equivalence point if the 40 milliliter sample is titrated with 0.7 molar HCl. So the pH at half equivalence point. So there's a reason why I have you annotate all of those titration curves, is for you to visualize what happens at half equivalence point. So here at half equivalence point, this is when your weak base equals your conjugate acid. And this is all based off Henderson-Hasselbalch. This is the equation on your equation sheet. Now, so you don't get confused, I know I wrote weak base and conjugate acid. I want you to just think that this is the basic component and this is the acidic. When you write pH equals pKa and all that stuff, it's based off something acidic. So the acidic thing goes on bottom, so the conjugate acid, and the weak base on top. Now, if you wanted to write the POH, you're more than welcome to, but we don't have to do that right this second. So, to figure all of this out, again, we are trying to solve for the pH. Now, if both of these equal each other, then here the log of 1 will equal 0. So essentially, this entire section will cancel out. So all that we're left with is pH equals pKa. So what we're going to do is there's actually, what's nice about all these equations, you can solve it in many different ways that you would like to, okay? There's one thing that we could do is using Kw, we can solve for Ka. That's one way of doing it. We could also try to find pKb, knowing that pKb will equal POH, and then do 14 minus that. Totally okay on how you would want to approach this problem. Here, I'm going to use the Kw equation. So this is true at 25 degrees Celsius. So if I'm trying to solve for Ka, this will be Kw over Kb. So 1 times 10 to the negative 14 over my Kb, which I just solved originally as 1.35 times 10 to the negative 3. If you do a different way, you could just take the negative log of Kb to get pKb. That also works as well. Both routes still get you to the same answer. So here, Ka will be 7.407 times 10 to the negative 12. Now that I have my Ka, I can get pKa, which is the negative log of Ka, so right above. Here, I get pKa is 11.13, which, looking at this portion right here, this will be what my pH is. So this is, again, will be true at half equivalence point, nothing else, okay? If you wanted to do the other route, you could have, again, you can think of, this would be Henderson-Hasselbalch based off of basic solution. So here you would have conjugate acid over the weak base. Here that also works as well because we know pH plus POH equals 14. We can still solve for pH. You could have done it this was the second route you could have done. But here I chose this route. Again, both get you the same answer, just different routes. All right, part B4. So here we want to determine the volume of 0.7 molar. This is going to be based off HCl. Required to reach the equivalence point. Forget something about equivalence point. Again, you're going to have to use the dilution equation, okay? So let's talk about everything about the weak base on this end and everything about the strong acid on this end. So we know concentration is 0.85 molar for my weak base. This is just from the beginning of the problem. And they told us volume is 40 milliliters. Then for our strong acid, they just told us the concentration is 0.7. And here we'll be solving for volume. So let's plug this in. Please note the volume units don't need to be in liters. They can stay in milliliters because if you think about it, the molarities will be crossing off. So whatever you get for V1 unit-wise, you'll get the same for V2. So divide by 0.7 by both sides. You get the volume as 48.57 milliliters or sig figs 49 milliliters. Okay. And then the last part, B5. We want to solve for the pH at equivalence point. So what's going to happen is we solved for volume and all that stuff, but this isn't really going to tell us much. If you're wanting to solve for a pH at equivalence, this is going to be a titration problem And you're going to first have to do a BCA table to see what is left. And then accordingly, based off what remains, if you have a buffer remains, we'll do Henderson-Hasselbalch. If it's just going to be in this sense, our conjugate acid remain, we will do an ice table. And then if our strong acid in this sense wins, we will just do a simple negative log of hydronium. So this, I'll just put objective 8.1, 8.2. This would be objective 8.3, or this will be objective 8.9. So these are our three options that could happen for part 2. But for part 1, we have to do a BCA table to see what is left. So let's write this. So again, this was a strong acid titrating a weak base. And here we'll have a conjugate acid, C2H5, 2, NH2 positive, making water. So you may or may not right now have already put pieces together of what happens at equivalence point based off what we talked about earlier. But here I want to talk about the math component. But here I will say this is not going to be a buffer and the strong acid isn't going to win. Here you're just going to have a conjugate acid, which this is the only thing that remains, because at equivalence point, your moles of strong acid equal the moles of the weak base. So if these are both your limiting reactants, this is what's left over. So based off the previous problem, we have all these molarities and volumes. I'm going to pause the video real quick just to show you some. So for the strong acid, I used the 0.7 molar and the volume at equivalence. I got moles as 0.034. And then for our weak base, I took that concentration and that volume. I also got 0.034 because think about it. This is equivalence point. The moles of the strong acid and the weak base equal each other. They're both 0.034. So to plug this in, our BCA table, and again, the whole purpose of doing the BCA table is to get rid of the things that reacted, because two things were added together, and we have to see what particles reacted and what do we have left, because the after will tell us how to approach the problem, aka part 2 of the problem. So here, 0.034, 0.034, none of this, no H2O. Here, and remember, we're in a BCA table, it's a moles table. And so here, this is not like ice table where we put minus X. We know which ones are limiting reactant. They both are, okay? So here, subtracting 0.034, no strong acid left, no weak base left, but we do make some conjugate acid because this is going to be one of our products. So this is what is left over. And that's what I was talking about in, part 1 of the 8.5 notes. If the only thing that remains is your conjugate in the products, we got to rewrite what is happening now. You just have a weak thing in weak equilibrium. This is objective 8.3. So I have moles, and this is a part that is overlooked by students. We just have moles, 0.034. This is not molarity. So we need to solve for the new concentration of our conjugate acid. So for C2H5, 2, and H2 positive, I have the moles left over. And we have to think there is a new total volume because two things were added together. So here, we're going to do 40 milliliters. And this is coming from the weak base. And then 48.57 milliliters, which is coming from this strong acid. I get 88.57 milliliters. Or we can convert it to liters, which we will want 0.08857 liters, that can be plugged in right here. I get my new concentration as 0.384 molar per conjugate acid. So now that we just have this remain, what's actually pretty cool is we're just going to flip the reaction. or think of it as you have a weak acid in equilibrium, and then we'd write water as a reactant. So here, C2H52, NH2 positive, less water. This is an acid, so it will donate the hydronium, and we'll be left with a conjugate base. Okay. So let's fill out our ice table. Because here we are solving for pH. We need to solve for what hydronium is to figure out what the remaining pH is. So here's 0.384 minus X. Then I have no water, 0, 0 plus X plus X. And now we need to do a Ka expression. So remember, Ka, we're going to take hydronium, multiply by this new conjugate base over our weak acid. Now here's the issue. We did actually solve for a Ka earlier, which we got 7.407 from earlier. Bring that Ka down here. So that was 7.407 times 10 to the negative 12 for our Ka. This is X squared, and then 0.384 minus X. And so now here we can take negligible X. So here, let's get rid of this because I'm not trying to do the quadratic. Then we have X squared over 0.384. Let's rearrange this. So this becomes X equals the square root of our Ka by the concentration of our conjugate acid. X is going to be 1.6865 times 10 to the negative 6 molarity. Well, it will be concentration, but here that X value, looking back up at the beginning, this will be what hydronium is, okay? So from here, hydronium helps us figure out pH. So pH is the negative log of that value. And I get my pH as 5.77. Now this should make sense that the pH is 5.77 just because we're talking about a weak acid. It should be something that's less than 7, and we were able to achieve that. And it makes sense that this would be the thing that remains, and this actually, in this case, would be our equivalence point, okay?